Howdy. In this video, we're going to go over a quick example on the equilibrium of a rigid body. This is obviously a problem in 2 dimensions, so it's subject to coplanar forces. Now, our job for today is going to be to determine the reactions at A and B. So let's take a look at the figure. What we have in this figure, we have this angled rod over here. It is pin connected at point A. Okay, if we go this way, we see that there's a distributed load. It starts here with magnitude 0 all the way to 80 newtons per meter. At the very end as well, we have this curved arrow, meaning we have a couple moment. The magnitude is 100. The units are Newton meter. This is going to be 1.5 meters away from this pin at A. If we look at the other end over here, this end measures 1 meter. It makes an angle of 30 degrees with the horizontal. And this end B of this bracket is making a point contact with this guy over here. Smooth contacting body. So how do we solve this problem? The first thing is going to be to do a free body diagram. So we'll start over here. The body looks something like this. Then there's a pin there, then it is straight. So that's the outline of the body. Next, we're going to put applied forces in moments. So in this case, easy one. I forgot here the little detail. Something like this. Over here, we have a moment of 100 Newton meters. So I'm just going to transfer over here to the bottom, 100 Newton meter. We have this distributed load over here. It's an applied load. However, it's gonna be best if we convert this distributed load into a single point load. Do you remember how to do that? Right? The magnitude of this distributed load is gonna be equal to the area over here. So if I have the area of this triangle, area is 1/2 the base, in this case 1.5, times the height, this is 80. This is going to be equal to, well, half of 80 is 40, times 1.5 is 60. So this is going to be equal 60. Look at the units, right? The distance, the base is in meters. The height over here is in Newton per meter. So meters cancels with meters, and this is the same thing as 60 newtons. So now we know how much. Where are we going to put this load? It's going to happen at the centroid. So the centroid for a right triangle is going to be 1/3, always from this right angle. So from this end that way is going to be 1/3 of the base. Well, if the base here is 1.5, 1/3 of it is going to be 0.5. So it's going to be 0.5 from this end this way. Or if I'm measuring relative to point A, it's going to be 1 meter. So at about 1 meter, I'm going to have the 60 Newton force over here. Again, that distance is going to be 1 meter. So from here to the force. Again, why 1 meter? It's 2/3 from this end or 1/3 on that way. So 2/3 of 1.5 is just 1 meter. So again, as we go through the steps of doing the free body diagram, I have here the outline of the body. I have applied load over here, 60 newtons from the distributed load. And I have a couple moment, 100 Newton meters at that end over here. Next, I need to add the reaction forces. So let's go alphabetically. At point A, I have a pin. So do you remember what the reactions are for a pin? Right, hopefully you remember that the question that we're trying to answer with the reactions is, we're asking the question, if something in the support is keeping the body from translating, then we need to count it with a reaction force. So if this bracket over here, this angle, it's pin connected. If I have it pinned here, would I be able to slide it here about the x-axis? The answer is no, right? Because that pin is going to hold it in place. So I'm going to need a reaction force in the x direction. Here I'm not going to think too much to predict what direction that force is going to be. I'm just going to assume it's going to go in the positive x direction. So we put the axes. This is going to be our x-axis, and pointing up is going to be the y-axis. Next, I need to ask the question. If this body is pinned here at this point A, could I easily slide or translate the body up and down? And the answer is no, because if it's pinned, the pin is going to hold it in place. So I need to put a reaction force. Again, I'm not going to think too much for now what direction that force is going to be. I'm just going to assume positive going up. So I have a y over here. Next question we need to ask is, does this support prevent any rotation? So if this body over here is pinned here, will the pin keep this from rotating or pivoting about point A? The answer, no, right? The pin is not going to restrict that motion, so I don't need a moment here. We're almost done, right? We look at the supports at A. Now we have the support at B. This is just a smooth contact. It's just resting on it. Do you remember what the reaction says? Reaction is for a smooth contact. Well, if you don't remember, we can get to it, right? How? Well, we're going to ask the same questions. If I'm making contact with this body over here, if it's a smooth, if there's no friction, would it keep it from sliding up and down? And again, when I do this, when I'm looking at point B, I'm going to forget that there's a pin over here. I'm going to ignore that. And I'm just saying, if I have something here just touching without any friction, would I be able to slide like in this direction? Yeah, no problem, right? If it's just touching here and I kind of push down on this, again, because they're not welded, I can move this bracket down, no problem. But if I try to move it up or against this guy, it's going to resist, right? So this guy's going to feel a force that is opposite. Always is going to be perpendicular, right? So it means we have a force like this. I'm going to call it force B over here. Not Bx or By, just force B, because I know this is going to be 90 degrees or perpendicular to the surface, because this is a smooth contact. The next question is, we took care of the translations. The next one is, if all I have is a point contact, like my finger here, and I got something resting on it, will it keep it from, maybe I can do it like this. Here's a point contact, here's a body. Will it keep it from rotating? And the answer is no, right? I can slide it like this, no problem. I can pull away. I cannot drive into, because if I do, the marker is going to feel force that direction, that's this one. But it can also rotate, no problem. So I don't need no moment there. So if we pause and look at this one, we're going to ask the question, can we solve this problem? And the answer is yes. I have 1, 2, 3 unknowns, right? And I have up to 3 equations of equilibrium. So I should be able to solve for this one. Let's see if you can remember what we discussed in the lecture. If this was the problem we're trying to solve, knowing that we have 3 equations of equilibrium, right? We can sum forces in the x, make it equal to 0. We can sum forces in the y direction, make those equal to 0. And we can sum moments about a point over here, A, B, so I'll just put it here, about a point of our picking and make it equal to 0. So in this example, when I'm looking at it, I want to analyze, okay, what do I have? I have unknown here, AX, unknown AY. I got 2 unknowns right there. So this to me is screaming, hey, if I sum moments at this point, these 2 are not going to create a moment there because the moment arm is 0. So I'm going to have one equation with 1 unknown, this FB over here. So if I sum moments at point A and make it equal to 0, we're going to go with our convention that counterclockwise is a positive moment. I'm going to look at A over here and I'm going to see, okay, does the force FB, can it create a moment about point A? Right? So if this guy is pinned here and I push down, will it make it rotate? The answer is yes, right? The force is FB, the distance, so what is the moment arm or the perpendicular distance between the force and this point A, right? From this free body diagram, I don't know, right? This means this free body diagram is not complete. I had the outline, the applied forces, the reactions, but I forgot the last step, which is including the geometry, any distances and angles. So I forgot to transfer down that this distance here is 1 meter and that this angle is 30 degrees. So now when I look at this free body diagram, again, when I'm solving these problems, I should ignore all of this. Now this is the problem that I'm trying to solve. It's a simplified problem. No longer I have distributed loads, I have point loads. Anyways, I'm looking for the moment. A moment is force, in this case FB, times a distance, that moment arm, which in this case is 1 meter. That's the perpendicular distance. Right? Next, I need to ask the question, will it create a positive or negative moment? So if I put my fist here at the point of interest, then I open up my hand over here and I go try to intersect that force. And then I curl my fingers in the direction of the force. So right now the force is pointing that way, so I have to go like that. Right? This is telling me with the right hand that this is going to be a counterclockwise moment. Remember, if you're doing this on paper, like this, that would be a thumbs up. That's a positive moment. Counterclockwise, it's positive. We don't need to, but I'm going to put a little plus there, just so I remind myself, hey, I accounted for the force, the distance, and the sign. Okay, so then I'm going to sweep from left to right, this is the first one. AX and AY, they pass through point A. They're not going to generate a moment. Their moment arm is 0. So the next force that can generate a moment is a 60 Newton force. So the force is 60 Newtons. The distance to that force is 1 meter. That's the perpendicular distance. So next question is, what is the sign? So I put my fist over here. I point my fingers in the direction of the force. And then I need a curl, right? I need to put my index in that direction of the force. Well, if it's like this, I cannot bend them backwards, right? I need to flip my hand so I can go like this, right? That's a thumbs into. If you're in the board, that's a thumbs down. It's a clockwise moment. That's a negative moment. So this is minus over here. So as I continue now, I have a couple moments, right? Same sign summing moments. Right, not only do I have to worry about forces that do not cross point A, but also any existing couple moments. In this case, I got this guy, right? Our convention is if it's counterclockwise, it's a positive moment. As drawn over here, this would be a clockwise or negative moment. So this would be minus 100. And all of these have units of Newton meter, Newton meter, Newton meter. The sum of all those three must be equal to 0, right? So I have one equation and I have one unknown. So I can solve for the force at B rather quickly. Right, I move this to the other side, move 100 to the other side, divide by 1. So FB equals 160 newtons. Notice this example, we have a positive number. Again, this was negative. I move to the other side, becomes positive. 100 is negative, move to the other side, becomes positive. Divided by a positive one, this is a positive number. Remember when we get a positive number for a reaction force, what it means? This means that the direction that we assume is correct. So we were correct in saying that the force is in that direction. So now we got this one. We still need to solve for AX and AY. How would you do it? And in this example, probably what the next easiest thing to do would be is just to sum forces in the X and forces in the Y direction. Why? Because AX and AY is in the X and Y direction. So if I sum forces in the X direction, right? If it points in that direction, that's the positive x-axis. So I'm going to say that's a positive force. So the first one that I have is going to be this one here. So force at B. It's going to have an x component. So an x component, FB x, and this guy's gonna have a y component, f, b, y. We need to calculate those, right? And if this angle is giving you any trouble, this is how usually I calculate the angles here. So first I'll draw my horizontal, and that's kind of crooked. Let me do it again, see if I can do any better. So I have the horizontal, which is just this axis, right? And then I have this angled portion of the bar, which is like this. It makes an angle of 30, so this angle is 30 degrees. Now we said this force FB is normal, right? It's perpendicular to this rod, so it makes an angle here of 90 degrees, like so. So if this angle is 90, this angle between this slanted line and this one is 90, so it means this guy has to be 60, right? And then if I draw a line vertical, x and y, between the x and the y there's 90 degrees, so it means this guy is 30. So to me that tells me, right, this is my force FB, that I have something that looks like this. This is FB. That's the x and the y axis. So either I can base everything off of this one. For example, if I want the vertical component, I can say cosine 30. I can also use this angle over here, which is 60, and it would flip it. But let's say I want to go with the 30 over here. Okay, FB cosine 30 is going to give me the side adjacent, that's the y component. In this equation, I'm summing the forces in the x. So really I want this guy over here. This is FBX, or the x component. So this is the force FB times the sine of 30. Right, so this would be FB times the sine of 30. That gives me this guy, but notice it's pointing towards the negative x-axis, so this is going to be negative. So we take care of this FBX. Next we have AX. It's pointing in the positive x direction. That's what I assume. So plus AX. This guy's vertical, and this is a moment, right? We're summing forces, so that's it. The sum of these two forces must be equal to 0. So we can solve for AX rather quickly by just moving this to the other side, right? So it's going to become positive FB times the sine of 30. Well, if FB is 160, 160 times the sine of 30 is going to be 80. So AX is 80 newtons. Notice again, this was negative, but I added to the both sides of the equation, right? So this is going to cancel, and I have it over here. This is positive. Positive means that the direction that I assume is correct. So I was correct in assuming that AX points to the positive x-axis. So I'll write my final answer something like this. The force in AX is 180 newtons over here to the right or towards the x-axis. Next, let's figure out AY by summing the forces in the y direction. So sum of the forces in the y direction equal to 0. Here our y-axis is pointing up, so any force that points up is going to be positive. I'm going to sweep this free body diagram from left to right. That's my just personal preference. Right, the first one that I'm going to have is going to be the y component of this force FB. Or if we look at this triangle, the y component of FB is going to be FB times cosine of 30 degrees. Notice that component is pointing down, so it's going to be negative, so minus. Right, that's the vertical. Then I keep on sweeping. Then I got this AY. I assumed it to be pointing up, so pointing up is positive, plus AY. Next, as I continue sweeping, I got this guy, which is vertical, but it's pointing down, so minus 60. And then at the very end, I got this arrow, right? It's not pointing down, it's curved, that's a moment. We're summing forces, so it's not going to show up in this equation. And there we have one equation with just one unknown AY, right? We already know what FB is. It's 160. So AY, it's going to be equal to, I'm going to move the 60 to the other side. So it's going to be 60 plus FB cosine 30. Where FB, remember, is 160. So 60 plus 160 times cosine 30. If I typed it in correctly, I get 198.6 newtons. Notice the answer is also positive. Move this, becomes positive. This was negative, move to the other side, becomes positive. So what that means is that, again, a positive number means that our initial guess is correct. So in fact, AY is 198.6 newtons and it should point up. So now let's look at the answers and see if these answers make a little bit of sense or not. Again, what we had over here was this angled piece of rod over here. We were putting a force down and then also trying to twist it in that direction, right? So look at that moment, we're trying to twist and also push down, which would also generate a twist. So this is telling us that FB is going to resist by putting a force in this direction. Now it's putting it normal, right? So there's a X and a Y component. So part of the force is trying to translate or slide the body this way. And that's why the X component is going to be towards the right. We need something to bring it back and keep it in equilibrium, keeping it from sliding this way. Also, this force is pointing down, and the B component is also, the Y component is also pointing down. So this one and that one, they're both trying to make the body slide down. That's why it makes some sense that this AY over here is pushing back up, restoring and keeping everything in balance. Now we have a lot of the important information. We have AX and AY, the X and Y components of the force at pin A, and we have the magnitude of the force at FB. So here, depending on how the question is asked, they might ask more information from you. Sometimes they want the X and Y components of the reaction forces. In this case, the ones at A we already taken care of. We will need to be able to, I need to calculate the X and Y components of this force over here, right? We will do so with the help of this triangle. So the X component of force B, FBX, right? We said already it's just going to be FB times the sine of 30. So we take 160 times the sine of 30. This is going to give 80. Oops. This gives 80. Notice FB pointing this direction. So it's going to be 80 newtons here towards the left. So we could write that component like so. To calculate the Y component, FBY, this is going to be equal to, we want the Y component, it's just FB cosine 30, right? So 160 times the cosine of 30 is going to be 138.6 newtons. That Y component of the force B is pointing down, so I'll put a little arrow pointing down. Again, this is in the case where they want the X and Y components of the reactions A and B. The other thing they might ask from you is to just calculate the force at A. So instead of expressing it with the X and Y components, actually calculating the resultant, right? So the resultant force at A, so force A is going to be equal to the square root of the sum of the components squared, right? So it's going to be the square root of 80 squared plus 198.6 squared. And this gives 214.1 newtons. That would be the magnitude of the force at pin A. Again, because we had X and Y components, that would give the resultant. The next thing that we need to do is to calculate the direction of that force. So let's make a quick plot over here, X and Y. The X component is 80, the Y is almost 200. So if I were to more or less put it to scale, X component like 80, and the Y is more than double, so 198.6. So that resultant, right, we can give this angle theta. Theta is going to be equal to the inverse tangent of what is opposite, that's my Y, so 198.6 divided by my X, or 80. Again, so if I type inverse tangent of 198.6 divided by 80, this gives an angle of 68 degrees. So the resultant here of A, like that, is going to have a magnitude of 214.1, and it's going to be at an angle of 68.1 degrees from the x-axis. I hope you found this video useful. If when you were following along you picked up on any mistakes over here, do let me and everybody know in the comments below. Otherwise, we'll see you on the next one.